Relative motion problems. These are kinematic problems dealing with vectors when you have more than one thing acting on an object on once. And what that means is if you have, say, a boat moving through water, the boat is applying a force to move forward, but the water is also applying a force to make the boat move sideways as current, or a plane through the air has wind blowing it. So we need a way to deal with the motion, the kinematics of these objects when more than one vector is applied to it. Now, there's really two main types of these problems that we're going to focus on this year. The first one is when we have an object that's moving in a direction, and then we have a constant force that is applied to them and makes them move in a slightly different direction. So what this looks like is a plane moving north like this. So there's our plane. And then we have a wind that pushes them east. So this purple line is the wind pushing them east. And what we're going to see is the green resultant vector. That is what the velocity is of the plane, the velocity relative to the ground. Okay? So if you were standing on the ground, if this was me right here standing on the ground, I would see the plane travel this green line as it flies because the wind is pushing it off course a little bit. That's type number one. Type number two is when we have an object that wants to move in a specific direction, but we know that there's going to be a force applied to them. So a similar example to this plane is we have a plane that wants to fly north, but there is a wind blowing east. So in order to counteract that, they have to aim into the wind. So if we start down here and we want to end up going due north, so this dotted black line, that's what we want. But we know that there's going to be this wind blowing east. So there is some type of wind blowing east. There's that green line, or that purple line, sorry. In order to fly, we have to aim into the wind so that the wind pushes us to move straight north. So we need to actually fly into the wind so that the wind pushes us straight and we move north. Okay. Now, I'm not gonna lie, this topic is pretty complicated. So the only way to get better at it is just to do practice, because it's just weird. But all it is vector addition. That's it. Still the same rules apply. Components, vector collectors, all that stuff is still exactly the same. So just a quick note before we try some examples. When we're dealing with planes, there's just some different terminology here. Whenever it says heading or bearing, that means the direction. Airspeed is the speed relative to the air. Ground speed is the speed relative to the ground. Wind speed is the speed of the wind relative to the ground. And the big one is if the wind says from the west, that means it's actually blowing east. So from the west means it's starting west and it's going towards the east. So just a couple things terminology-wise to keep in mind. So let's try an example. So we've got Professor Chaos flying his Evomobile, takes off and flies due north with an airspeed of 200 kilometers an hour. Shortly after takeoff, strong east wind of 70 kilometers an hour picks up. What's Professor Chaos's resulting velocity? So the ground speed. Okay, so this is very similar to the question we were just talking about. We've got a plane traveling north at 200 kilometers an hour. Then the wind shows up and starts blowing east, okay? And that's 70 kilometers an hour. And we want to know what is the resultant velocity of those two vectors, okay? Now, this is a nice right angle triangle because we're dealing with just east and north. So we don't really need a vector collector, but if we did use a vector collector and we looked at the components of this, well, the plane originally was not going in the x direction, but was all in the y direction. The wind was all in the positive x direction, none in the y direction. So this resulting velocity is going to be 70 in the x direction and 200 kilometers an hour in the y direction. And what that looks like is a nice triangle. If we start off at our 0 point origin, we're going 70 in the x direction, 200 in the y direction, and our resultant velocity looks like that with some angle. Now, we can solve this using trig, which gives us an answer of 212 kilometers an hour at an angle of east 71 degrees north. Now, if you wanted to do this question, but just with the original triangle, we would have a different angle that we'd probably look at right here, because this is our original starting point. The only difference, right, we just found this 71 degree angle right here. We would find this to be 19 degrees, okay? But north, 19, east. It's exactly the same question, okay? So this is just a vector question, but just with some words attached to it now, okay? The second type of question is when we have a boat that wants to go in a specific direction, but we have some other force acting on it. So in this case, we have a boat that's trying to cross a river that has a current of 5 kilometers an hour moving east. The boat wants to go from the south shore and land exactly across the river from where they start. So we want to figure out what angle should the boat aim at in order to move directly across the river. So we have a boat that is starting on the south shore and wants to end up directly across from it on the north shore. But we have this current pushing east, which means this boat has to aim along this brown line here so that the current pushes it directly across. Now, I kind of messed this question up. This 9 kilometer an hour in still water fact was supposed to be up here. So we're going to use this in part A as well. When these questions tell you a boat can move in still water or something like that, or a plane in still air, that means without anything else acting on it, that's how fast this object is going. So if there was no current and we decided to point our boat in this direction, we would travel along this brown vector at 9 kilometers an hour. But the current exists, which means we are going to travel at a slightly different speed because we are fighting against the current a little bit. So part A asks us, what angle should we aim the boat? Okay, well, this is just a triangle, right? This is just a nice right angle triangle because we're going directly across. We've got a current moving directly east. It's not always going to be right angles, but this north-south line and this east-west current line makes a nice right angle. So in this triangle, just be careful of your trig. We're looking at this angle theta. We're going opposite over hypotenuse. So the inverse sine of 5 over 9 gives us 34 degrees. So we're aiming at north, but we're swinging 34 degrees towards the west. Or if we're talking about rivers, this is also called upstream, where we have to aim 34 degrees upstream so that the current pushes us and we move straight across. Okay. For part B, we're figuring out how fast does the boat go relative to the shore. So if we were on the shore watching this thing, how fast is this boat actually moving? That is our green vector in this picture up for part A. That's how fast we are actually moving across the shore. We're not moving at 9 kilometers anymore because we are fighting against the current a little bit. So when we do our Pythagoras, 9 squared minus 5 squared, that gives us 7.5 kilometers an hour relative to the shore. And it's because we're fighting against the current. Not all 9 kilometers an hour of our speed is going to crossing the river. Some of it is going to fighting against that current. Okay? So these are the two types of questions that you'll see quite a bit. Question number 1 here, you move straight across, you've got current or wind pushing you to the side, so you start to move at an angle. Versus moving at an angle originally, the current pushes you back so that you end up moving straight. Kind of the reverse types of questions, all right? Now, There's a ton of different other variations that are all slightly different from these ones. They all involve vectors. They all involve some type of vector collector and looking at components. We're going to do a couple more examples in class, and we're going to look at some implications of this relative motion, these vector problems. So we'll do a little bit more in class. Hopefully these two questions got you going and could give you a little bit of a head start with this stuff. If you want to try some practice on your own, I would suggest skip this independence of direction. We're going to do that together in class. But try some of these examples down here. These are all going to be very similar to what we just did with little slightly different, maybe more angles. So try some of these questions and we'll go through them more in class.